Alright, let's go and take a look at question number 2. Let region R be the region in the first quadrant bounded by the x-axis in the graphs of ln of x and 5 minus x shown in the figure above. Find the area of R. Okay, so if I'm going to find the area of R, before I even begin this problem, what I probably want to do is I probably want to put both functions into the calculator, and I've already kind of done that here. And so next thing I'm going to want to do is I'm going to want to find those points of intersection. So how do I do that? Well, I'm going to go to Menu, and I think you guys have already seen it, but Menu, Analyze Graph, Intersection, left bound, right bound. It's this 3.69344 number. And so I'm going to go and write those down. I'm going to reposition those. That way I can use them a little bit more quickly here. So my points of intersection are going to be 3.69344, comma, 1.30656. Okay. So we found the points of intersection. I think this is going to be really important information later on in this problem here. So as I move through this, I'm going to go ahead and reposition these. I'm going to call this M, and I'm going to call this N, just so that I can move a little bit faster. Now, if I'm going to find the region of R, like the problem's actually asking me to do, what's funny is that I tried this earlier. If I use the bounded area function in the calculator, if I start off at 1, for some reason it gives me all of this stuff. All right, and that's not helpful. If I put in 5 being the upper limit of integration, it gives me this bounded area. I don't want that. Right? I really don't want that space. So I'm going to go ahead and not do it that way. And so if you end up in a situation like this where you are clearly not getting the area that you want, clearly this is going to be the wrong answer, just go about it the old-fashioned way. I mean, like realistically, we have to set it up anyway. And so a couple things to note. F1 is my ln of x, and then F2 is my linear function, so that's going to play a role when I go to integrate this thing. And so as I go to set this up, I'm going to go goodbye to the calculator for a second. As I go to set this up, there are a couple of other things that are not particularly straightforward about this problem. Usually, area between curves involves some kind of top minus bottom action. There is, if you notice, there is no top and there is no bottom. That's particularly clear in this problem here. And so you can attack this a couple of different ways. You can either switch everything to dy, right, and solve this, make this e to the y, and make this whatever this thing becomes y minus 5. And then you can do right side minus left side. That's cool. That's a lot of work. What I'm going to do instead is I'm actually going to separate this into 2 different regions. And we're going to draw a nice little line straight down. Okay? Now what does that do? It splits my integral, because now what I have is I just have curve space on the left side. And on the right side I just have linear space. Okay? And so that's how I'm going to set up this integral. It doesn't really matter how you do it. The rubric takes either way. I'm going to integrate from 1 to m. M being this breakpoint number here, this 3.69344 number. And when I do that, I'm only going to be evaluating the ln of x. Right, because that's all this space underneath the curve only. And then I'm going to add that from m to, looks like 5, of my 5 minus x dx graph. Alright, so let's see what that turns out to be. So if I do my shift plus, I'm going to go from 1 to, what was m again? 3.69344. Whoopsie. 3.69344. And remember, the curve was the f1, right? So this is going to be f1 of x dx, and I'm going to add that to another integral. Now, if this was a non-calculator problem, I'd probably just ask you guys to do a triangle. Honestly, since we have a calculator, just go ahead and do it regularly. Just going to double check my numbers, make sure that I'm good. It's 3.69344. 3.69. 3, 4, 4. Gotta fix that. And that's going to go to 5, and this is my linear function, which is f2 of x dx. So from here I just hit Control Enter, and I get my number. Cool. So it's 2.9. I'm going to go ahead and split screen this thing here. It's 2.9 to 2.985, blah blah blah. Okay, so let's go and write that down. So it's 2.9858. All right. Very cool. So that's pretty straightforward. I mean, the only thing you got really we got to keep in mind here is to make sure we split our areas or switch everything to dy. It doesn't really matter which way you go. Part B. Region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is a square. Write but do not evaluate an expression involving one or more integrals that gives the volume of the solid. Now, one of the advantages of doing Part A the way we did it is Part A is literally Part B. We just got to finagle it just a little bit more finessing involved. I'm still going to go ahead and do 1 to m, and my first integral is still going to be ln of x dx. But because each piece sticking out is going to be a square, the ln of x just gives me the base length. I need to multiply it by a second ln of x to get my height, because in a square, I'm just going to illustrate this real quick. If each cross-section was a square and this was ln of x, then the other ln of x would have to be the height. So that's what gives me the area of the square. The dx gives me the width, and there's my first integral. So after that, I'm going to go ahead and do it with the other piece. So from m to 5, and that's going to be 5 minus x squared dx. And notice how it says, write but do not evaluate. I think Part B is done. Very cool, very cool. All right, next. It says the horizontal line y equals k divides region R into 2 regions of equal area. Again, write but do not solve an equation involving one or more integrals whose solution gives the value of k. So how do we do that? Well, one of the disadvantages of doing A the way we did is because now we're doing a horizontal line y equals k. So I'm going to go ahead and just draw this horizontal line across, and it seems to split this into 2 regions of equal area. Okay? And so if I'm going to be evaluating some kind of area, that means that my area is actually going to be moving in this direction. So which means that it was inevitable. I would end up having to write these as y functions after all. So let's go ahead and do it. If y equals ln of x, that means that x is equal to e to the y. And if y equaled 5 minus x, that means that x was equal to 5 minus y. Okay, so these are the 2 functions that I'm going to be using in Part C now. Okay? And so I know that the horizontal line y equals k divides R into 2 regions of equal area. This word is really important. Equal area is really important, meaning what we're going to do is when we evaluate this integral, if I go from 0, right, 0 being the bottom portion of this function, or the bottom portion, that's where I start, I'm going to have to evaluate up to k. Well, where's k? I have no idea. I doubt it's there because I don't think these are equal areas, but k could be anywhere on this graph that would divide the region up into 2 equal areas. Well, since I'm doing a dy integral, what I'm going to want to do is I'm going to want to look at right minus left. And so what does that look like? Well, the right function is my linear function, so that's going to be 5 minus y. Right? And again, since we're just finding area, there's no coefficient on the outside, there's no squared, no nothing. And if I evaluate just 5 minus y, well, what do I get? I get all that space, right? Trouble is, I don't want all that space. So I'm going to get rid of this space. How do I get rid of something that I don't like? Well, I'm going to go ahead and subtract this little space right here, which is the space between, this is the minus, space between e to the y and the y-axis. Alright? Now, here's the thing, is that if I was to solve for k, I know that what this area gives me, because we've solved this before, we've solved this in part A, this gives me 2.9858. But because the area from 0 to k is only 1/2 of that, because the area from 0 to k divides into two regions of equal area, this thing needs a 1/2 on the outside. So, in case you guys are wondering just what the heck happened, let me reiterate what just happened. If you look back to some of your multiple choice and you look at solve for the value of k that makes the function, the integral equal 16, if you remember those questions, you basically just set up one of those in part C here. So basically, if you were to solve for k, you would integrate this expression as it was. You'd plug in a k wherever you see a y, and you would know that that integral, that definite integral, would equal 1/2 of this number. Okay? Cool. That's it for number 2. We'll see you in the next one.